linear equation, and then we discuss how to find the solution. Right? We have to reduce the system of we have to convert the system of equation to the matrix equation Ax equal to b, and then we have to find the solution. Now there are some more methods to reduce the system of equation. So today we are going to discuss the important definition, reduced row echelon form. So definition, row echelon form. So definition, a row echelon form or echelon form. So echelon form, a row echelon form of an augmented matrix, of an augmented matrix, is of the following, So given any matrix, we have a row echelon form. So what we have to do some process in the given matrix, you will get a row echelon form. So what in row echelon form, I will explain here. So the following form. Okay. So the first one is, if you take any row, okay, first one, the zero, suppose if the matrix contains some zeros rows, then you have to transform it to the bottom of the row. So the zero rows, if it is there, so if there is a zero rows, if they exist, then we have to come the last in the order of the row. So we have to, suppose in the matrix the first row itself zero row, we have to take that row into the last row. So come last in the row, in the order of the row, order of the rows. Okay, that is the first thing we have to do. So if a matrix contains any zero rows, maybe 1 0 rows or 2 zeros rows, we have to take all the zeros and the last rows, okay, at the bottom of the rows. Next, second things we have to do, if we take the first non-zero entry of each row, the first non-zero entry of each non-zero row. So non-zero entries of the non-zero rows, because non-zero rows only contains non-zero element, right? So the first non-zero entry of your non-zero rows should be 1. Non-zero rows are 1. If it is not equal to 1, then we have to make that first position should be 1. That is, we have to that non-zero entry is called leading one. So it's called leading ones. So that is, if you scan each row, if suppose we scan the rows from left to right, if you found the first non-zero entry, that entry should be 1. Okay, that entry is called the leading ones. Each row you have to scan. Okay, from left to right we have to scan. If you found first non-zero element, that element should be 1. If it is not equal to 1, we have to do some elementary row operation. We have to make that element should be 1. Next, the third thing, what is the condition for this one? If once you find the leading entry, the below the rows should be 0. So below each leading ones leading one in the is a column of zeros. That is, suppose we have matrix. Suppose you have scanned the first row. Suppose everything 0. Suppose we get some non-zero entry here, that should be 1. That is the second condition. And once you find the non-zero entry, below the all the columns below the entry should be 0. That is the first, second, third condition. So once you find, if you suppose you scan the first row, the first entry, suppose you are getting 1. That is the second condition. If it is 2, you have to make that position is 1. Okay. So the first non-zero entry of each row should be 1. Maybe the non-zero entries appear in the third position, or maybe here also they maybe appear. That is not an issue. But if it is appear, that element should be 1, and then below the columns of the corresponding. So suppose you're getting 1 here, so the below the column should be 0. Suppose you are scanning the second row, suppose you will get some non-zero entry, and then first entry should be 1 here, that the corresponding column should be 0. Okay. So again, if suppose scanning the third row, suppose you are getting some non-zero entry here, maybe some elements may be here, that is not a problem. But below the diagonal should be 0. So sorry, below the leading entry should be 0. That is the third one. So below each leading ones is a column zeros, column of zeros. Thus, okay, erase this one. Thus, in any two consecutive non-zero rows, the leading one is in the lower row appear further to the right the leading upper ones. So that is what I am saying. So the leading ones, the leading one in the lower row appears further to the right, then the leading one in the upper row, That means, suppose you are scanning, suppose we have a matrix. Okay, suppose we have a matrix, there are some rows. Okay, suppose this is first row, second row, third row, and so on. Suppose we have first row, you are scanning the first row, you got to find the non-zero entry. Suppose you are finding the non-zero entry here. Okay, that entry should be 1. Okay, suppose this is 1. Suppose you are scanning each row. Suppose you are scanning the first row, you will get some non-zero entry in the third position. Okay, so suppose you are getting 1 here. Therefore, the before suppose 1 getting here. Therefore, previous element should be 0. Okay, so this is a leading one. Okay, don't bother about this, but the corresponding column should be 0. Once you find the leading ones, the corresponding column numbers are 0. Now we can scan the second one. What I am saying, suppose you are getting 1 in the previous row, you are getting in the third position. Okay, this is the first position, this is second position, this is the third column, right? Suppose you are getting the previous row, getting the leading one is in the third position, then R2 should be the non-zero position after 3. Maybe here 4th position or 5th position or 6th position, but after third column only the non-zero column should appear. So suppose R2 appear some non-zero entry the first position, that is not a echelon form. Okay, that means you have to compare with the previous row. If suppose the previous row appear the non-zero entry the third position or third column, then R2 should be the non-zero entry should be after the third column. Maybe 4th column it is appear, or 5th columns maybe appear, anything. But after third column the non-zero entry should be appear, and then below the diagonal should be 0. Okay, and then again you are scanning R3. Yeah.
Then for R2, first and second position should be 0, sir.
Yeah, the first so once you find so in the R1, suppose you are finding the first non-zero entry the third position, the previous element should be 0, because this is the first non-zero element and that element should be 1. Again you are scanning R2, you are finding the first non-zero element maybe somewhere here, but that is not equivalent form. So when we say a matrix is equivalent form, so that non-zero leading entry of the second row should be after third column. So therefore previous entry should be 0. So for example, if you take the identity matrix, so identity matrix is 1 0 0 0 1 0 0 0 1. So now I scan the first row. Where I found the first non-zero entry, the first entry itself, and then the corresponding columns are zero. Okay, good. Now I did the first. Now we got to scan the second row. We found the first non-zero entries here. Okay, and then this non-zero entry appear in the second column, because the first row contains the first non-zero entry appear in the first row is first column, but if you scan the second row, it should be after first column. Yeah, clearly we get after first column. Therefore, the corresponding columns are zero. Below the entries are zero. Now we scan the third row. You'll get the first non-zero entries here, and this entry should be after the third column. We have to compare with the R2. So R2 appear the one in the second position or second column. Therefore, R3 should be the non-zero entry should be after second column, maybe third column or fourth column, because here there is no fourth column. Therefore, definitely this is a row echelon form. Okay, so otherwise, suppose if you take some other matrix, so suppose I'm taking some 3 by 3 matrix 1 0 minus 1 0 0 1 0 0 0. Is this echelon form, row echelon form? First, we have to scan the first row. Okay, where we find the first non-zero entry, the first entry itself is a first non-zero entry, and it should be 1. Therefore, satisfy the first condition. It should be 1, and then below the diagonal should be 0. Yeah, below the leading entry should be 0. Therefore, 0 0 is there. Now we did the first row. Now we have to scan the second row, where we'll find the first non-zero entry here, and this first entry is non-zero entry should be 1. Okay, now it is appear after the third column, because after the first column, because we found the first non-zero entry in the first row is here. Maybe we can find a non-zero position in the second column or after the second column. Now here we get third column. It's not a problem. And below the diagonal should be 0. Sorry, below the entry should be 0. Is satisfied. And look at the third R3 column, but R3 there is no non-zero entry. Therefore, everything is 0 entry. Therefore, it should be in the bottom of the matrix. Therefore, this is a row echelon form. This matrix is called row echelon matrix, because satisfy all the conditions. Each row we got to scan. That is the first condition is, if it is 0 rows exist, you have to transform that row into the bottom of the row, or bottom of the matrix. Suppose, therefore, all the other rows are non-zero entries. Now we have to scan one by one row. First, you scan the first row by left to right. If you find the non-zero entry anywhere, that should be 1. That is the first condition. Every non-zero entry of the non-zero row, that should be 1. If it is some other number 2 or 3, that is not a equivalent form. We have to make that entry should be 1. Okay, so that is the second condition. You have to scan each row,
okay,
and the non-zero entry should be 1. Yes.
Yes, sir. I understood, sir.
Okay. Now third, what is the third point is, below the each leading entry should be 0. The column elements below the leading entry should be 0, and then the leading entry in the lower row, the leading one in the lower row should appear farther to the right than leading ones. Suppose in the first row appear 1 here, you are not allowed to take the leading entry. The second row cannot be here. Okay. So why that is called the echelon form in military, or if you take any NCC parade or anything. So suppose one row, one person, the second person, and so on. There is some row, and then the second row should be start from here. So that is called the echelon. Okay, and then the third row person start from after this, maybe start from here, this position. So therefore, this is actually echelon form. So if we take any NCC parade or any parade, it should be the rows should be like this. So the first, but the once you find the position, the first row, the first position here means the second row, the first position should be after this position. So maybe this is first position, this is first position, second position, this is third position, and so on, nth position. Now the first row, the first position, the first person appear in the first position, but in the second row, the first person appearing after one, maybe in the second position or third position. Suppose the first person appear in the second position in the second row. If you look at the third row, the first person should be appear in the third position or fourth position or anything, but it's not equal to, not a second position, not a first position. So this is a echelon form. So like this decreasing order. First person and the second row should be here, and then third row should be the non-zero entries here, and then the fourth row means the non-zero entry should be here. So before this everything zero. Okay, this is actually echelon form. So that's why we call this echelon form. So this is actually row echelon form. So a matrix is said to be row echelon form, then it satisfies three conditions. That is, if it is any zero rows, that zero should be a bottom of the matrix, and every non-zero entry of each row should be one, and then below the leading entry, we call that element is leading one, and then the below the leading one should be zero. Okay, and then uh, the lower leading ones in the lower row appears farther to the right than leading the first upper row. Okay, so that is if the matrix satisfies these three properties, then we say the matrix is a row echelon form. And another definition is a reduced row echelon form, or sometimes called row reduced echelon form, or sometimes called reduced echelon form. So what is the extra condition we have to add is that above the leading end is also zero. It should be a row reduced form. And what is the extra condition that? But in the row reduced in the row echelon form, below the leading end should be zero, but in the reduced row echelon form, above the leading entry should be zero. The columns, corresponding columns also. So this is the definition of a row echelon form. Now we have to add the one more condition to this. It becomes a reduced row echelon form. So maybe I can write here the definition. The reduced row echelon form. The reduced row echelon form. Otherwise, sometimes called row reduced echelon form. Okay, echelon form. Actually, sometimes is called row reduced echelon form, RREF. Okay, row reduced echelon form or reduced row echelon form. So row reduced echelon form of an augmented matrix augmented matrix. Augmented matrix is of the following, is of the form. It should be row echelon form, and then so above the leading entry should be zero. So maybe I can write the fourth point. We have to take the first 3 points for this definition. The fourth point should be above each leading ones should be zero. Leading ones is a zero column. Columns should be zero. Columns of zeros. In addition to row echelon form. In addition to a row echelon form. Echelon form. So for example, if we take some example and then we will say which one is row echelon form, which one is reduced row echelon form. So maybe you can take some examples. We have some matrices. Suppose I am writing here 1 0 0 0 1 0 0 0 0. This is the first matrix. Suppose I am taking the second matrix is 1 2 0 3 6. Not that 6 actually. This is 3 6. And then 0 0 1 1 1. And then the next one is 0, 0, 0. Everything 0. Now I'm taking this 1, 3, 2, 6, 0, 1, 1, 0, and then 0, 0, 1, 3. Suppose this is our, suppose we have three matrices. Now, which one is row echelon form, which one is row reduced echelon form or reduced row echelon form? Now, look at the first matrix. Now, we have to scan, look at the any, first we have to check any non-zero rows are there, as any zero rows are there. Now, we have zero rows, therefore, we have to take that zeros in the bottom of the matrix, therefore, 0, 0. Therefore, we did the first condition. Now, second condition, we have to every non-zero entry. Now, every non-zero rows. Therefore, first row is a non-zero row. Why? Because some non-zero entry is there. That is a non-zero row. Now, we have to scan the each row. First, we have to scan the first row. Where, suppose we find the first entry, first non-zero entry, that should be 1. Now, this is the first non-zero entry. That should be 1. And then corresponding, the columns are 0. Yeah, it is 0. Okay, next we have to scan the second one. The second, if you scan the second row, the non-zero entry should be after the first column, because already we found that the previous row we found the first non-zero entry is the first position, first column. Therefore, if you scan the second row, the first non-zero entry should be either the second column or third column, but not in the first column, because already we said that this is one. Okay, now we scan the first we scan the second row, we get the first non-zero entry here, and then it should be should be 1. Okay, is satisfied. And then below the columns are 0, below the leading entries are 0, is satisfied the second condition. And you no need to scan the third column, third row, because it's already 0. Therefore, this is row echelon form, right? Now, it should be row reduced echelon form or not. Only thing we have to check that once you find the leading entry, the above the columns are 0. So in the first leading entry is this one, but there is no above. This is the first column. This is the first row. Therefore, no need to check. This is the above the columns are 0 or not. But in the second row, so this is the leading one. So above the column is 0. Yeah, it is satisfied. But in the third row, there is no 1, there is no leading entry, therefore no need to check the third row. Therefore, this is RREF, that is row reduced echelon form, the first matrix. Now look at the second matrix. Now we have to, again, if it is any 0 rows, we have to make take in the bottom. Now we have 0 rows here, we have to take in the bottom. Now we have to scan the first row. We find the first non-zero entry, that should be 1. Yeah, we get a first non-zero entry in the first column itself, and it should be 1. Therefore, satisfy the first condition. And then the corresponding columns below the leading entry, it should be 0. Yeah, below the leading one should be 0. Yeah, satisfied. Okay, now we scan the second row, and we get a first non-zero entry here, and the position should be after the first column. Yeah, anyway here we get a third position or third column, right? Therefore, and then below the leading ones is 0. Yeah, it is satisfied. And then no need to check the third row, right? Because already 0. Therefore, this is row echelon form matrix. Now we have to check this is a reduced row echelon form matrix or not. That means what? Above the leading one should be 0. So we have only 2 leading ones, that is 1, and then is we have only 2 leading ones, namely it is appear in the first column and then third column. Now we have to check the above the leading entries, the columns are 0. If you take the first row, there is no above the columns, therefore no need to check. But in the second row, this is the leading entry, and the above the column entries is 0. Yeah, we have 0 here. And the below 0 is nothing but that is a row echelon form. It's already, we already checked. And this is therefore this is a row reduced echelon form, because we no need to check the third column, third row, because everything is 0. Now look at the third matrix. Now here there is no 0 rows, therefore we have to start from the second point. We have to scan each row. So first you scan the first row, where we'll find the first non-zero entry in the first column itself, and it should be 1. Yeah, it's okay. And then corresponding columns are 0. Yeah, it is okay, 0. Therefore, we did the first row. We did the scanning of first row. Now we scan the second row, and the leading entry should be after the first column, because already we We found that in the previous row, we found the first leading entry in the first column. Therefore, if you scan the second row, the leading entry should be after first column, maybe second column or third column already. Anyway, we get here the first non-zero entry, leading entry, and should be 1, and it is appear in the second position. And then below the leading entry 0. Yeah, it is okay. Okay. Therefore, we did the second row. Now we scan the third row. Again, the first non-zero leading entry we get here, it is appear in the third position. Yeah, okay, because the previous row, it is appear in the second position. Therefore, the next row, the non-zero entry should be after the second position. Here we can, is in the appear in the third position. And here there is no below the diagonal. So anyway, this is a, therefore, this is a reduced echelon form. Okay, but this is not row reduced echelon form. Why? Because if you take the second row, this is the leading ones, but above the leading ones non-zero, but we need 0. But here 3 is non-zero number. Therefore, again, even if you take the third row, above the leading ones, we are given non-zero entries 2, 1. Okay, therefore, the last matrix is not reduced row echelon form, but it should be reduced echelon form. Sorry, row echelon form, but it's not reduced. So reduced means what? Above the leading ones also 0. So any doubt in this?
No.
So,
No,
yeah.
sir.
So, yeah, that is very important too, because why we need this row echelon form, row reduced echelon form is that, so in the previous, we have to solve the system of equation. So I already said that we have to try to make more entries are 0. It is enough to, we have to reduce the given augmented matrix of the system. We reduce into the either row echelon form or reduced row echelon form. Once you reduce to that, the given augmented matrix into one of either a row echelon form or row reduced echelon form, we can easily solve the problem. Because look at this, because we get so many zeros in the entry in the matrix. Okay, so that's why we have to reduce the given augmented matrix into reduced row echelon form. It is even better. Okay, suppose we are reducing the row echelon form is okay, but you are reducing a row reduced echelon form, then is still better. So therefore, this is very important in this system of solving equation. So which matrix is row echelon form, which is row reduced echelon form, all the things you should know. Okay, maybe if possible, maybe we will do some problem, and then we will move to the next one. Okay, so next we start solve some problems. We solving system of equation. Okay. So maybe problem 1 is solving system of equation by Gauss-Jordan elimination method. But anyway, actually we are going to convert that into row reduced to echelon form. Okay, just I write the equation. So x1 plus 3x2 minus 2x3 equal to 3. This is the first equation, and then second 2x1 plus 6x2 plus or minus 2x3 plus 4x4 equal to 18, and then x2 plus x3 plus 3x4 equal to 10. So there are 4 unknowns, x1, x2, x3, x4, and then 3 equations. Therefore, if you transform the, what is the matrix equation, so we have to write the coefficient. The first row, the x1 coefficient 1, x2 coefficient is 3, x3 is minus 2. There is no x4, therefore 0 in the first row. Second row, we have x1 coefficient is 2, x2 coefficient is 6, and then this is minus 2, and then x4 is 4. And then third row, there is no x1, x2 is 1, x1 is 1, x3 is, x4 is 3. So this into x1, x2, x3, x4. There are 4 unknowns variables equal to the right hand side values 3, 18, 10. Okay. So this is our matrix A. So therefore we write in the matrix form AX equal to B, where A equal to this matrix, and this is A, and this is our capital X we call, and this is our capital B is a column vector. Now this is a matrix equation. Now what is the augmented matrix? So we have to write the augmented matrix is nothing but you have to merge this column vector to the matrix B, matrix A. So what is the augmented matrix? Nothing but so we have to so 1 3 minus 2 0 2 6 minus 2 4 and then 0 0 3. This is A. Now we have to merge this B, that is 3 18 10. Okay, the last column we have to merge it. Now we have to make this matrix, we have to reduce this matrix into row reduced echelon form. Okay, therefore first you have to check that there is no zero column, so there is no zero rows. Therefore you start from the second thing. What we have to do? So first you scan the first row, you get 1 here. Therefore, what we have to do, we have to make the below the leading ones are 0. So therefore, we have to make this position 2 should be, we have to make should be 0. And what we have to do, we have to add or we have to multiply -1 to the first row and then add to the second row. We will get this this position should be 0. Okay. So therefore, this is equivalent to saying that. So I am keeping the first row now. But now the second row I am going to replace it. What I am going to replace? I am going to multiply -2 the first row and then adding to the second row. So we have to add. So we have to R2 second row minus 2 times first row. Therefore, if you multiply first row by 2 and then subtract. Okay. So therefore, this position is 1. If you multiply by 2, 2 minus 2 is 0. Therefore, this position is 0. Now here we have a 3. If you multiply by 2, we get 6. 6 minus 6 is 0. And here we have a -2. If you multiply by if you multiply by 2, we get a -4. But we have to subtract from -2. All minus is there. Therefore, minus plus. Therefore, we get 2. And this position we have to multiply 2 by this position. Anyway, 0 is there. 4 minus 0, we get 4. And 18 minus 2 times this is 6, actually 12. Okay. Now we make this. Now we keep the third row. So 0, 1, 1, 3, 10. Now we did some part. Now what we have to do? We have to scan now. Anyway, we have to interchange this third row and then second row because we have some 1 here. So anyway, we can interchange the second row and the third row. Therefore, I can keep the first row 1, 3, -2, 0, 3. Now I interchange the third row into the first row, second row. That is a row elementary row operation. This is one of the interchanging the columns. So interchanging the rows also a elementary operation, row operation. So therefore, we have to make the second row into the third row. So in this question, what in this is I am we are replacing R2 implies R. So we have to interchange R2 and R3. Now we scan the second row. We get a non-zero entry after the first column. After the first, because already we found that the first leading entry is appearing in the first column. Therefore, the next row contains the leading entry after the first column. Now, if you scan the second row, you will get a first non-zero entries here, and it should be 1. Okay, and then below the leading one 0. Okay, we did it. Okay, now we have to scan the third row. We get a first non-zero entries here, but this is not equal to 1. Therefore, we have to make this position is 1. Therefore, we have to divide 2 to the entire row. Okay, so that is the next thing we have to do. Okay, so next equivalent, we have to keep the first row and then second row. Okay, so first you have to reduce the matrix into row echelon form. After that, you have to reduce to row reduced echelon form. So first we have to reduce into echelon matrix. That is row echelon matrix. Now, what I am going to did for R3, we have to did R3 by, you have to multiply by 1 by 2. We got to divide by 2 to the R3. Therefore, this is 2. If you multiply by 1 by 2 or divide by 2, we get 1. And 4 by 2 is 2. 12 by 2 is 6. Okay. Now, is this row echelon form? Now, finally, we get some matrix. Is this row echelon form or not?
Yes, sir.
Yeah, because it satisfies all the things. But it is not a reduced row echelon form. Why? Because the second row,
Because above
the
one
leading
we
entry
have
is 1,
to
but
use.
this entry is non-zero. Similarly,
Sorry.
for this leading one, the above the columns are non-zero. Therefore, this is not row reduced echelon form or reduced row echelon form. Okay, done. But we have to make this matrix into reduced row echelon form. So then what we have to do? Now we have to make what we have to make. We have to make that which position is 0. We have to make this position should be 0. Because first row is not a problem, right? Because 1 is here, above the 1 there is no rows, therefore no need to check for the first row. Now look at the second row. We have to make the above the leading entry should be 0, but here the leading entry is 3. We have to make this 3 is 0. Then what we have to do?
So multiply second row with -3 and then add
Yeah,
it.
yeah. So therefore, I am keeping the okay. Now I am going to replace the first row by, I am going to multiply second row by 3. That is 3 times R2 minus the first row. So anyway, here 0, 3 times 0 is 0. Okay, anyway, so this, okay, multiply by -3 and then add to this one. That's why, otherwise we get -1 here. Okay, so that's why I take some, we got to multiply the second row by -3 and then add to the first row. Therefore, we get 1 here. Here we get 0. And what is the position here? Here we have to multiply -3 here. Therefore, -3 -2. Therefore, -5 here. And this one is -9, and this one is -30, -27. Okay, I'm correct? Yeah, if I make any mistake, please correct me. So we can keep the first, now we keep the second row, it's not an issue. So 0 1 1 3 10. Can you have to keep the third row, 1 0 0 1 2 6. Now what we have to do? Now look at, now scan the second row is satisfied because we found the leading entry in the second column. Above the leading, below the columns also 0. Right? Okay? Therefore, because this is the leading one, above the columns are 0, below the columns are 0. Therefore, we did the second row. Okay. Now look at the, scan the third row. This is the leading one, but above the leading ends are non-zero. Therefore, we have to make that 2 position should be 0. We have to make the above 2 position should be 0. Then what we have to do? What operation we have to do? Again, we have to multiply 5 to this row and then add to the first row. Because this 5 and then this -5 is 0. Therefore, first row, anyway here 0. 0 times 5 is 0. And then we have to add to the first row, we get 1. And then this 0. If you multiply this 5 and then plus 5 minus 5 is 0. And if you multiply 5, this is 10. We are going to add to this one, therefore we get 1. And if you multiply by 5 here, therefore 30. 30 plus 27 is 3. Okay, now we did the part. Therefore, just I am writing what we did. So I am going to replace the R1, the first row is by, you have to multiply 5 to the last row, that is third row, and then I'm going to add to first row, and then we have to replace. Now what we have to do the second row. Second row also we have to do this position, we have to make 0, right? Therefore, just to subtract from second to third. So therefore, I am going to replace by second row by R2 minus R3. If you take R3 minus R2, we get -1 here. So So therefore, this minus the R2 minus R1, therefore 0, and this is 1. This 1 minus 1 is 0. Here 3 minus 2 is 1, and this 10 minus 6 is 4. Now we can keep the last row. Now we finally, is this reduced row echelon form?
Yes, sir.
Yeah. Okay. So finally, so actually what I did, the last column is the left hand side. So therefore, if you write in the matrix form, so the corresponding matrix form is 1 0 0 1 0 1 0 1 0 0 1 2, right? And this into x1 x2 x3 x4 equal to 3 4 6. Now if you product this first row, this x1 1 into x1, that is x1, plus 0 into x2 is 0, finally we get just x4. So x1 plus x4 equal to the first entry is 3, and second x2 plus x4 equal to 4, and then the last one is x3 plus x4 equal to, sorry, 2 times x4 equal to 6. Now we can rewrite this. You can rewrite the first equation. You can keep x1 equal to 3 minus x4, and then the second equation we can write x2 equal to 4 minus x4, and then the third equation, because everything have a x4, right? So therefore this x3 can be written as 6 minus 2 times x4. Therefore, we can, here we have a one free variable. We can choose x4 is any value. Okay. So there is no other condition on n. There is no condition for x4. Therefore, x4 is the free variable. So actually, how to find the free variable, number of free variables is nothing but number of variables minus number of equations. So number of variables or unknowns in the given equation minus number of equations. But here there are 4 variables, x1, x2, x3, x4, and the number of equations 3. Therefore, 4 minus 3 is 1. So we have to take one variable is free variable. So free variable is what? We can take any value, either x1 or x2 or x3, take any value. But here we can take, there is no condition on x4. We can take x4 is any value, 1, 2, 3, minus 1, minus 2. Take any value, we get x1, x2, x3 value, because all the threes are depends on this one. Therefore, solution, if suppose I am writing the solution, is always a 4 tuple x1, comma x2, comma x3, comma x4 is nothing but, if you take x4 equal to t, I am taking some value t. Therefore, what is that? X1, 3 minus t. What is x2? 4 minus t. What is x3? 6 minus 2t. And then what is t? What is x4? T. So this is a solution. If you give some values on x4, we get solution. So now we easily we find a solution. Therefore, so if you reduce the given matrix into row echelon form or reduced row echelon form, we can easily solve the problem. Okay. Now, question is, suppose I already said that if the right hand side is 0, then we say the system is homogeneous system. So in a homogeneous system, the number of unknowns is more than number of equation, then it has infinitely many solutions. So maybe state the theorem. So if you take, okay, so what I am saying, suppose if you consider the matrix equation Ax equal to 0. So can you say one solution for this? And already we said that trivial solution, x equal to 0, if substitute x equal to 0 is always trivial solution. But how many solutions exist for this system of homogeneous equation? That is a theorem. Okay, the theorem says, suppose the number of unknowns is more than number of equations, then it has infinitely many solutions. So that is a theorem. So if a homogeneous system if a homogeneous system has more unknowns or variables, unknowns, more unknowns than equations, number of equations, then it has infinitely many solutions. Then the system has infinitely many solutions, not only trivial solution, it has other solutions also. So infinitely, sorry. Infinitely many solutions. So if the number of unknowns are more than number of equations, then it has infinite many. So only for homogeneous system, not for non-homogeneous system. Okay. Okay. So I hope everyone know about the matrix addition, the matrix multiplication, all the things, right? Sum of the matrix, product of the matrix, all the things, right? Upper triangle matrix,
Yes, sir.
diagonal matrix. So I assume that one. So and then we move to the, and then we know the properties of matrices. Okay, so A plus B plus C is nothing but A plus B plus all the things, you know. Okay, suppose quickly some the transpose of the matrix, right? So you can interchange the rows into columns, columns into row. That is a transpose of the matrix. Okay, now some special definition, some special type of matrices is symmetric matrix and then skew symmetric matrices. Okay, so definition, you already know that one. So anyway, a square matrix is said to be, a square matrix A is said to be symmetric if A and its transports are equal. So a square matrix A, this A is different from this A. Okay, so a square matrix A is called, or A is said to be symmetric. A matrix is symmetric if A and its transports are equal. Okay, okay. Or we say skew symmetry. A matrix set to be skew symmetric if that A equal to minus A transpose. Okay, so the symmetric matrix and the skew symmetric matrix are very important matrices. Why? Because any matrices we can write sum of symmetric and then skew symmetric matrices. Okay, now so this is a definition for symmetric and then skew symmetric matrices. Now the properties of transpose. So what are the properties we know? If you take transpose, if you take any matrix A, if you take transpose, again you take the transpose, you will get the original matrix A. So A transpose is nothing but A. Suppose you are adding two matrices A plus B and then taking the transpose is same as, you have to find the transpose of individual matrix and then sum, both are equal. A transpose, A plus B whole transpose equal to A transpose plus B transpose. And then third property, suppose we have some scalar k times A, that means you have to multiply each entry of A by k is some scalar, and you are taking the transpose same as multiply a scalar into A transpose, that is k times A transpose. This is the next another properties of transpose. And then what about even if you take subtraction also? So A plus B, instead of plus you take minus, you will get minus here. So A minus B transpose is nothing but A transpose minus B transpose. Therefore I can write plus or minus. Okay. So the next one is product of two matrices. Suppose I am taking A and B and then take the product and then take the transpose. Is same as first you take the B and then take the transpose product with the A transpose. So B transpose A transpose, not A transpose B transpose. And then already we know that two matrices never commute. Okay, in general, A and B two matrices, then A B need not be equal to B A. It's not satisfy the commutative property. You got to keep in mind. So for some matrices satisfy the commutative property, but in general, two matrices not satisfy the commutative property. So these are all properties of transpose. Okay, so A transpose nothing but A. A plus or minus B transpose equal to A transpose plus or minus B transpose of this. Now, using this property, we can show that if we take any matrix A, we can write sum of symmetric and then skew symmetric matrices. Take any matrix A, we can write sum of two matrices B plus C. And this B is nothing but symmetric matrix. We can find some symmetric matrix and we can find some, this C is skew symmetric matrix. So any matrix, any square matrix, we can write sum of symmetric and then skew symmetric matrix in a unique way. That means only one symmetric matrix, only one skew symmetric matrix for any matrix A. So actually that matrix B is nothing but A plus A transpose by 2. So I am taking this is our B. We are going to show that this B is a symmetric matrix. Why? Because if we take the B transpose, so what is B transpose? Is nothing but A plus A transpose by 2 whole transpose. We are taking transpose both sides. Now 1 by 2 is a scalar, so we know that we can take outside. And then A plus A transpose nothing but A transpose by the property A transpose whole transpose. Because A plus B whole transpose nothing but A transpose plus B transpose. Here A equal to A, B equal to A transpose. Again, we know that A transpose is nothing but A. Therefore, 1 by 2 A transpose plus this is nothing but A. And A plus B equal to B plus A. So we know that 1 by 2 write A plus A transpose. So this is nothing but B. We take B equal to this. Therefore, this B satisfies the condition B equal to B transpose. Therefore, this B is a symmetric matrix. Now, if we take C equal to A minus A transpose by 2. Now, this C is skew symmetric matrix. Why? Because we find what is C transpose. It's nothing but A minus A transpose by 2 whole transpose. Again, you can take 1 by 2 is a scalar, you can take outside and then apply the property A transpose minus A transpose whole transpose. So this is nothing but 1 by 2 A transpose. A transpose nothing but A. Okay. Now we can take minus outside. Therefore, we get minus 1 by 2 times A minus A transpose. If we take minus outside, then this should be. Now this is nothing but C. Therefore, minus C. Therefore, C satisfied the property that C equal to minus G sun. Therefore, this C is a skew symmetric matrix. Now just add these two. What is B plus C? So B is nothing but A plus A transpose by 2 plus C is A minus A transpose by 2. We can take 1 by 2 outside. So therefore we get A plus A transpose plus A minus A transpose. We can cancel this A transpose and then A plus A 2A and then 2 cancel, we get A. Therefore the matrix A can be written as sum of two matrices. One matrix is symmetric matrices, another matrix is skew symmetric matrices. Okay, so this is very important. So any matrix, any square matrix is a sum of symmetric matrix and this skew symmetric matrix. So actually this part is symmetric part of A and this part is called skew symmetric part of A because every A have two parts. If we take complex number, it's a real part, imaginary part, right? So because any complex number is equal to, we can write x plus iy, right? So this x is called real part, this y is called imaginary part. So similarly here, any square matrix we can write sum of symmetric and then skew symmetric. So B is a symmetric, C is a skew symmetric, then B is called symmetric part of A and then C is called symmetric part of A. Okay. So any square matrix can be written as sum of symmetric and then skew symmetric matrix. That symmetric matrix is nothing but A plus A transpose by 2 and then the skew symmetric is nothing but A minus A transpose by 2. And then there are, we can easily check that. Suppose we have to show that is question. Suppose A is a square matrix. A into A transpose. Is this symmetric? Is a symmetric matrix or not? So therefore, we have to check that the transpose of this matrix you have to show itself. So therefore, you take the transpose, what you'll get? This is equal to, by the definition, product of two matrix transpose is nothing but the second matrix transpose into the first matrix transpose. Okay, but A transpose nothing but A into A transpose. So therefore, we get the A transpose is, we call some matrix B. B transpose equal to B. Therefore, it's a symmetric matrix. Therefore, it's a symmetric matrix. A into A transpose is a symmetric matrix. Then what about A transpose A? Is this symmetric? We will check. So we have to take the transpose equal to, apply the definition, A transpose into, because the second matrix transpose into the first matrix transpose. So first matrix A transpose, and then you take the transpose. Therefore, A transpose into A transpose nothing but A. We get the same matrix. Therefore, A transpose A also symmetric. If you take any square matrix, A into A transpose is symmetric. A transpose A is also symmetric. So you should know how to check a matrix is symmetric or not. You have to take the transpose and then apply the properties of transpose. You get the same matrix or not. Okay. So these are all some properties of transpose. Now, in general, so our aim is to find the solution of the system of equation. Okay, so there are three cases. Maybe the system have a solution, or if it is solution exists, maybe only one solution exists, or infinitely many solutions exist, right? Therefore, if we take any system, the one of the following is true. So what is this? So we make state as a theorem. If you take any linear equation, maybe it's a homogeneous or non-homogeneous, that is not a matter, but it is always, so any system of linear equation. So any system of linear equation has either no solution, maybe solution does not exist. If it is exist, maybe it exists only one solution. That is exactly one solution, or exactly one solution, or infinitely many solution or infinitely many solution. So any linear equation have either no solution or exactly one solution or infinitely many solution. There are only three possibilities for any system. Now, how to check the system has no solution, system has unique solution, system has no infinitely many solution, all the things. Maybe I can write here. It's very important. So keep in mind. So before that, anyway, I will say what is the rank of the matrix. Okay. So rank of the matrix is nothing but, you studied in the school days, number of linearly independent rows of a matrix. It's so very difficult to understand, find the linearly independent rows. So better definition is, so now we found that given any matrix, okay, so suppose A is given, A is a given matrix, we have to do some operation, we will get some matrix that is row reduced echelon matrix. Any matrix we can do some elementary row operation, finally we reduced into row reduced echelon matrix, right? Now we define the rank of the matrix is, so maybe we call that the row reduced echelon matrix is what we call R. R means the row reduced echelon matrix of the matrix A. Okay, so otherwise something we can, somebody write the notation RREF of the matrix A. That means what? Row reduced echelon matrix form of the matrix A we call R. Okay, so this is very RREF of A. Otherwise, simply I am saying REF of A means what? Row echelon form of A. It is a different matrix, but you get that matrix from A using some elementary operation. Okay. RREF means what? Reduced row echelon form of the matrix A. Okay. So now we define what is the rank of the matrix. So rank of matrix, we write the notation rank of A. So in school definition, what we studied in terms of in school days, we didn't study the row echelon form, right? So therefore we studied the definition number of linearly independent rows. So linearly independent rows. So it's not number of non-zero rows, okay? So don't confuse with this. So number of linearly independent rows of A. In a matrix A, how many linearly independent? So therefore the word linearly independent is now, it's not clear, right? So therefore don't use this definition now. Now we defined a new definition using the row echelon form. So therefore rank of the matrix A is nothing but number of non-zero rows, number of non-zero rows in the echelon form, because every matrix have a echelon form. Given A, we can find a row echelon form, row reduced echelon form. There are two matrices we can find from the given matrix, usually called RREF of A, RE of FA. Okay, that is given any matrix, we can find we can reduce that matrix, we get some row echelon form or row reduced echelon form, right? So we take a row reduced echelon form, and then we got to find the number of non-zero rows in the reduced row echelon form, we defined as a rank. Reduced row echelon form. So number of rows in reduced row echelon form of A. Any matrix A, we have row echelon form. In that, we have to find the number of rows. That is, we define rank of the matrix. Okay. So far in the previous example, if we take the examples we did here, right? So this is a original matrix A. Okay. So now this is our A. What is the rank of the matrix? So we have to check the number of, there are three rows are there. Therefore, we have to check number of linearly independent rows. It's very hardest to find. Therefore, we have to reduce this matrix. We finally reduce the row echelon form, except the last row, because this is augmented matrix. So just to remove this last column, we have to look only this matrix. Now we have to find the number of non-zero rows. The first row is non-zero, second row also non-zero. Okay, yeah, this is a row echelon form, right? So therefore we have three non-zero rows. Therefore we define rank of the matrix is A equal to 3, because the row echelon form of the matrix A. So this matrix, so we found this matrix, right? So this matrix is nothing but what? RREF of A. This is nothing but RREF of A, because this is the row echelon form matrix of the given matrix. We finally reduce this. So in this matrix, we have to find the number of rows. So number of non-zero rows is 3. Therefore, rank of the matrix is 3. So that is our definition. So got it? So rank of the augmented matrix means we got to check this. Take the entire matrix. So this is rank of the augmented matrix. So fine. So how we define the rank of the matrix? You have to reduce the given matrix into the row echelon form, and then you have to find the number of non-zero rows in the matrix, and then we define the rank. So from starting A, after elementary row operation, we get a row reduced echelon form of the matrix A. We get some other matrix, maybe we call R. Yes.
So, but this way will be a long way to find the rank.
Yeah, but time being we define this rank, but we will define some other way. Okay.
Okay, sir.
Okay. Anyway, both are equivalent definition. Okay. Rank of the matrix is nothing but number of linearly independent rows. So that is very difficult. You would find the number of linearly independent rows. It's very hard. It's very difficult. Not difficult, but it takes time. Same thing here. This also, you have to reduce the matrix into the row echelon form, and then you got to find the non-zeros, the number of non-zeros. But time being, we assume that this is the definition. Now, after we introduce the linear transformation, vector space, all the things, we define a rank of the matrix is some other way. But this is the original definition. All of the definitions are equivalent definition. Okay. Anyway, so keep in mind. So anyway, you can use any definition. You can use first definition or second definition. So suppose you are able to find the number of linearly independent rows, you can do that definition. You can take that definition. Suppose you are
Okay.
suppose I am easily reduce the matrix into the row echelon form, then you reduce that matrix and then find the rank. So up to your wish. Which one is easy, you can take that definition. But linearly independent, even if suppose you are work with A itself, means you have to find the number of linearly independent rows, not number of rows. Okay, so that is careful. Now we define what is mean by rank of the matrix in two different ways, either number of linearly independent rows or number of non-zero rows in the row echelon matrix of row echelon form of the matrix. So there are two definitions. Either you can use that one or this one. Now our aim is to state that when the system of equation have a no solution, does not have a solution, have a exactly one solution, have infinitely many solution. That is very important. Now I state that formula or condition, you can take anything. Suppose we have a system of equation. Okay. Suppose I take n equation, n variables. So I am taking ax equal to b. That is our system. Okay. So that means I am taking A is a suppose m by n matrix. So that means what? There are n unknowns, m equations. So that is actually meaning, right? So we have this is m by n, and this should be x should be n by 1, right? Then only we can take the product. You will get finally you get m by 1. So therefore the number of variables here is nothing but n. So it's nothing but the number of columns in the matrix is nothing but number of variables, and the row is nothing but number of equations. So that is a things. So suppose I am writing the matrix form, the system of, suppose I am saying this Ax equal to B is the system of equation. So the number of variables is, and A is a n by n matrix, then this n is the number of variables, and this n is the number of equations. Okay. So now, what is the condition that, suppose I erase all the things. So suppose we have system of m equations, n unknowns. Therefore, the matrix equation Ax equal to B, the A is a m by n matrix. Then when this system have a solution, a unique solution, and then infinitely many solution, we will discuss now. Okay. Suppose I am taking here. Let A is a m by n matrix. And consider this equation, the system of equation, matrix equation, Ax equal to B, where x equal to is a 1 by n by 1 matrix. Okay, so 1 by n vector, column vector matrix, and B is a m by 1. Now, therefore, A is a m by n matrix. Therefore, what is the number of variables? Number of unknowns are variables. Number of unknowns is n. Number of equations is m. That is a system of equation. So the system of equation contains n unknowns, that is x1, x2, etc., xn. The equations are m equation. Now we call we call this system is equation number 1. Okay. When this equation number 1 has solution or exactly one solution or no solution, suppose I am writing here different color. Okay. So suppose first one, if the rank of the matrix A, not equal to rank of the adjoint matrix, augmented matrix, that is A adjoined with B. So this is augmented matrix. Okay. Suppose rank of these two matrices are not equal, then there is no solution. Then the system 1 has no solution, does not have a solution or no solution. If both rank of the matrix A and the rank of the augmented matrix both are not different, then the system has no solution. Suppose both are equal, That is second one. Suppose if the rank of the matrix A equal to rank of the matrix, the augmented matrix AB, both are equal and it should be less than n. So n is nothing but number of unknowns. Okay. So if it is less than n, it has infinitely many solutions. Then the system 1 has infinitely many solutions. Has infinitely many solutions. So solution, what is the guarantee to solution exists? The rank of the matrix should be equal to rank of the augmented matrix. And if it is less than n, n is nothing but number of unknowns. If it is less than n, then the system has infinitely many solution. Suppose equal to n, then it has a unique solution. So that is third one. So if rank of the matrix A equal to rank of the augmented matrix, and this is both are equal to the number n. N is the number of unknowns in the system. Then the equation, the system 1 has unique solution or exactly one solution. Exactly one solution. So very, very important. So therefore, if you know the rank of the matrix A and the rank of the augmented matrix A, from that we can conclude that the system has a solution or not, it's a unique solution or not, it has infinity solution or not. Okay. So this thing is very important. So n is nothing but here number of unknowns. How many variables in this system have? So that is our n. So you have to check these three conditions, and then we can conclude which one is happen, and then the system has a unique solution or not. So any doubt so far? So if it is given, system is given, so suppose they are asking the system contains a unique solution or infinitely many solutions or exactly one solution, but you have to check this one of the conditions. If it is rank of A and then rank of augment of A, if it is both are equal, then solution exists. It is unique solution if it is equal to n. If it is infinitely many solution, it is less than n. Okay. So we try to find the rank of the matrix. Now look at the previous problem we solved here, right? So now the question is, what is the main problem? So this is our problem. Now, how many solution this system have? So is the solution exist or not? If it is exist, how many? It is only one or infinite many? Okay. So that is the question. Now what is the answer? Based on theorem. Now what is the rank of A? And then what is the rank of augment of matrix of A? Now, so this is matrix A up to the first three columns. So this is rank of first you will find the rank of A, and then augment means you got to join this column. So what is the rank? Suppose you use the first definition, you have to find the number of linearly independent rows. Otherwise, you can use the row reduced echelon form. Finally, now we found that. So this is a row echelon form matrix of A by B, augmented matrix. Now, if you take only the first four columns, that is rank of A. So here we have 3. Rank of A is 3. What is the rank of the augmented matrix? You got to take full matrix. Again, here is a row echelon form of the augmented matrix. Again, the rank is nothing but number of non-zero rows. Again, 3. 3 equal to 3. Therefore, solution exists. But what is the number of variables? Is 4. But 3 is less than 4. Therefore, it has infinitely many solutions. That's why we get the solution here. If we take any values of x4, we get a value. We get a solution. Therefore, here rank of the matrix is 3. The rank RA, or we can just call RA or rank of A is 3. Rank of the augmented matrix AB is also 3. Therefore, both are equal. Therefore, definitely solution exists. If it is not equal, solution does not exist. But anyway, here equal. And these two values are, what is n here? Number of unknowns. The number of unknowns is 4. x1, x2, x3, x4, right? Therefore, these two values less than 4. By theorem that the system have infinitely many solutions. If it is equal to 3, then it is a unique solution. But anyway, in this case, the number of unknowns is 4. Therefore, it is strictly less than 4. Therefore, the infinite solution are here. If you give any values of t, we get the infinite many solution, right? So t varies any number. Therefore, this result is very useful to check that a system have a solutions, infinite many solution, or unique solution, or no solution in terms of rank. Okay, so any doubt? Otherwise, we can stop now. Thank you.